last week, we finished up last week talking about the measurements of how we talk about an average, or what did we specifically call it? We specifically called it measures of central tendency. In other words, how do we tell about what the central part of whatever set of data is? And we had three different ways. First was the mean, which is the average everybody knows. The second was the median, which was what? What was the median value in a set of values? The one in the middle. Or if there are two in the middle, you average those two. But that's how they get median. And then finally there's the mode, which is what value? The one that happens the most. There could be more than one mode if you have two pieces of data that happen the same amount of times, or there could be no mode if all the pieces of data are single values or the same number of values. Okay? Tonight we're going to talk about, this is section 12.3, section 12.3, and we're going to talk about measures of dispersion. Okay, measures of dispersion. What do I mean by that? Let's say we had three different values. Let's say we had 10, 20, and 30. What's the average of those values? Average is 20, right? 10 plus 20 is 30, plus 30 is 60. 60 divided by three values is 20. Oops. Right? The average, X bar, is 20. Okay? What if I said the values were 1, 20, and 39? What's the average now? 1 plus 20 is 21, plus 39 is 60. 21 plus 39? 21 plus 39, 0, 1, 60. 60 divided by three values, X bar equals 20. What's the difference between having a set of 10, 20, 30 and a set of 1, 20, 39 when the average is the same? Are there differences between those two sets? Yes. What are the differences? Yeah, the distance between the numbers. Yeah, dispersion, right? So the distance between those numbers is the important part of this. Okay? So, in other words, if we were to graph the, well, it's tough to think about graphing these in general, but these numbers are all closer together. You could have three numbers, 20, 20, and 20, and the average is still 20, but there's no dispersion here. In other words, the numbers are not far apart at all. Whereas 1, 20, 39, the numbers are much farther apart, and then 10, 20, 30, they're somewhere in the middle. So that's what we're going to talk about tonight. Okay? We're going to talk about how dispersed the data is. Okay? Questions on that? All right. We have two things that we can talk about. Okay, we can talk about the range of values, and this weird thing called the standard, not the start, the standard deviation. Okay, standard deviation and the range. The range of data is simply the difference between the highest and lowest. Range. Difference between highest and lowest. Really, really easy. When we had 10, 20, 30, what's the range? 30 minus 10 is 20. 30 minus 10 equals 20. So whatever the top value of the lowest value was. If we had 1, 20, 39, what's the range? What is it? It's not 20. The range is the top minus the bottom. So 38 in this case. Okay, the range is now 38. And if we had 20, 20, 20, what's the range of that one? 20 minus 20 is 0. That's the range. It's just how much difference there is in the total absolute spread of the values. That doesn't mean the range tells you that much about these things. 10, 20, 30, 30, 30, 30. What's the range of those ones? 30 minus 10 is 20, and the same for this one. But lots more values, and the average of this one's much higher, right? So range tells you something. It doesn't tell you that much. It just tells you the difference between the lowest and the highest. All right. That's the range. Okay? All right. So if you were to look on page 700 in your book, you don't have to now, but I'll put up. If you were to look at page 700 in your book, you would see a chart that shows the number of workers per country for 5 different countries. Okay? It looks like this. The number of chart is this is in millions. Okay? And you've got a bunch of names here and a bunch of countries down here. 778, and then 472, and then 107, and then 82. And if I want to find the range of those numbers, what's it going to be? 778 minus 82, which is 8 minus 2 is 6, 17 minus 8 is 9, 696, right? 696 what? Millions. Yeah, million workers. Okay, that's the range. Easy stuff. Okay. All right. The standard deviation, okay? What the standard deviation means is more or less the, how should I put it? It's kind of the average distance something is from the middle. Okay, you don't have to write that down necessarily. Here's what it means in terms of a formula. The standard deviation, and it's this another one of these crazy formulas, kind of like the mortgage ones. Okay? It's the standard deviation of the sum of the value minus the average value squared, and we'll go through lots of examples of this, divided by the total number of samples minus 1. Hopefully this is exactly what's on your sheets on the bottom of the formula sheet, okay, where it says standard deviation. Okay? S in this case stands for standard deviation. I'll show you how to use this in a second, but what this means, again, is if you take a whole bunch of values, if the standard deviation is small, that means most of the values are probably right around the same point. Okay? Most of the values are right around the same point. Okay, so here's the other stuff I handed out tonight too. And one other. There you go. If the standard deviation for something is large, it means that the average value, or the normal value of those, or I should say, most of the values aren't necessarily around the same place. Here's an example. If I was to give, when I give you guys a test, okay, if most of you guys got in the 90s, let's say you all got like around between 90 to 95 or something like that, that would have a small standard deviation, meaning most of you guys are doing roughly the same. Teachers actually like a small standard deviation in general, because that means at least everybody's right about on the same page. Now, if some of you guys are getting like 98s, and then some of you guys are getting like 28s, nobody is. But if people were getting like 98s and 28s, and there was a whole range in between, the standard deviation would be very large. Teachers generally dislike this because it means some students are going to be boarding class and know it all, and some students are going to really struggle. And for a teacher, who do you teach to? The really struggling ones, or the ones that are doing great, or somewhere in the middle? It's tough. It's a tough thing to do. So standard deviations are kind of bad. Here's how this works, okay? First thing you do is, number one, you find the mean, okay? If the mean shows up in your formula, you better know what that number is. This is if you have a whole set of data, okay? We'll do some practices on this, okay? The second thing you do, this is what takes a little bit longer. You find the difference between each value and the mean. In other words, if the values were 10, 20, 30, the first thing you do is you find the average. So what's the average of 10, 20, 30? 20. because you do 10 plus 20 plus 30 divided by 3. Okay? And then for the first one, you'd say, I might write them like this, 10, 20, 30. Right? You would say x minus, this is x minus x bar, which means your value minus the average. So 10 minus 20 is negative 10. 20 minus 20 is 0. 30 minus 20 is 10. And you have to do that for all the values that you have. By the way, this is a very good thing for a computer to do. Because if you have lots of values, a computer can really quickly do this. But you with your calculators can't do it really quickly, necessarily. Okay? Alright, so that's the second part, find the difference. The third part is, should have done it like this. We'll do it like this. One, there we go. The third one is that you square the difference. See how in here, this whole thing is squared? Okay? I'm going to write an arrow there so I don't have room to put it. I'm going to write x minus x bar squared. Okay, what's negative 10 squared? 100. What's 0 squared? 0. What's 10 squared? Also 100. Okay? 100, 0, and 100. Okay, so we're going to square the differences. Okay. Our fourth step, well, remember what this little symbol meant? I mentioned it last week. Remember what that means? Sigma? The sum. Okay, it means add all these guys up. So number 4 is add the squares. You add the squares. Okay, well, let me add the squares over here. 100 plus 0 plus 100, 200. That's this step. Okay, adding the squares. Okay, 5. Divide by 1 less than the number of items. Okay. So now we're going to have 200 divided by, there's 3 total items, so it's going to be 3 minus 1 is 2. 200 divided by 2 gives you 100. Okay? And then finally, what's the last thing we do in this whole thing? It's the big giant thing around everything. Take the square root, okay? Take the square root. Sorry if that's too tiny to read. Take the square root. Okay, the square root of 100 happens to be 10. That's your standard deviation. What this means, and this is actually not a bad example because if you look at here, what's the average distance between values?
10.
About 10, right? From 10 to 20 to 30, in fact, exactly 10 in this case. Okay? This says that the standard deviation is the average value between those two numbers is going to be 10. So this formula figured it out for us. Okay? We'll do another example. I'll erase some of this. We'll do another example where you can practice this, okay? Which brings me to, let me remind everybody who is supposed to have a calculator. Everybody bring theirs if they've got it. Who's supposed to have them? Okay? Jacob, Ace, Zach, Sterling, Adam, Wing, Clay, Christine, Timur, and Oliver. Anybody not have one that should or wants to borrow one tonight? You want to borrow? Are you going to have one for the test next week?
Yes.
How about you? You got one as well or no?
I'll borrow one.
Okay, I only have one to borrow. We'll have to figure something out for next week. You guys don't get share. You got a share for now? That one?
Yeah.
Okay, I don't think I have any others. All right. Let's do another one. Okay. Here are the values I'm going to give you. I'll leave the numbers up there. The values I'm going to give you are going to be 17, 18, 19, 20, 21, and 25. Okay, let me write those down. 17, 18, 19, 20, 21, and 25. One of these is not like the other in terms of its sequence, right? Let's find the standard deviation for each of these. In fact, it's probably better to write them down, so I'll do that. 17, 18, 19, 20, 21, 25. I'll start writing down what I have on these, and you guys can do it. Of course, I don't have a calculator of my own. Do it on the computer's calculator. That's what I got. I might have done it wrong though. Some of your calculators may actually have a standard deviation function on it. I don't think the blue ones do. And you probably shouldn't use that for the test, but it's on your calculator, it's on your calculator. And you have to figure out how to use it though. You have to type in some special things. Anybody else get 2.83? Oh, good. No? Which step did you not get to? Did you get this? Did you get all the numbers? The X minus? You got X bar first, right? 20. Got that first?
Why you brought it up?
No. 17, 18, 19, 20, 21 plus 25 divided by 6, 120. 120 divided by 6 is 20. Once you guys get the average, then you can do each individual number minus the average. Boom, 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 boom. Then you take the squares of them all, add up all the squares, hopefully get 40. Take 40, divide by 1 minus the total number of items, which gives you 8, and then take the square root of 8, which you get 2.83.
So it has to be a decimal.
It doesn't have to be a decimal, but
You can't do like 2 square root of 2.
yeah, you could do 2 square root of 2. But the answers normally for standard deviation are going to be a decimal. Yeah. If you want to write 2 square root of 2, that's cool. Find the difference between the mean. So you know the mean is 20 now, right? Okay, what's 17 minus 20? Negative 30. 18 minus 20.
We divide it.
Okay. The back row. You guys all figured this out? Standard deviation? You know how to do it? Okay, you guys? Still working? Okay, give them another minute. For those of you who didn't get this, or who got it done, I wrote down something up here, and I just want to do, this is the kind of thing you might want to, where this might make a difference for, just like kind of a real life example. Let's say you guys wanted to invest some money in something, and you have a choice to invest it in U.S. securities, in other words, U.S. companies or something, or Asian companies. Okay? If you look at the investment over the last 10 years, or 1998, 2008, if you had invested in U.S. securities, it would have been 11.2% return, okay, per year. If you'd invested in Asian securities, it would have been 19.5% return, okay? Well, given those numbers, it looks like you should just go for the Asian securities, right? I made these up, by the way, the standard deviation. Let's say you also have some information about each year. In the U.S., you had a 27.3% standard deviation from that 11.2%. In other words, up and down some value. Let's not make percent. Let's say it's going to be, I don't know, 2.5% standard deviation, or 3.5% standard deviation, 3.5% standard deviation. Well, this is the part that you say, okay, it looks like the U.S. securities don't fluctuate as much versus the Asian securities. Again, I made these values up. But you might want to take that into consideration if you're going to go investing money. You might say, well, if I'm only going to invest money for a year, well, it looks like Asian securities might do better, but I have a bigger chance of losing this year because the fluctuations are greater for the Asian securities. Okay, that's where standard deviation might come into play. Okay? Better annual return, but more risk is really what it comes down to. More risk from the other one. So you got to take those kinds of things into consideration. Okay? I will leave you with this on page 704 in your book. Look at the standard deviation pictures, figure 12.8. Okay? What it does is, as you disperse farther from the range gets bigger, the standard deviation gets bigger as well. Okay, keep that in mind. All right. Okay, listen, let's take our first break. Because you guys were here doing the stuff, you were on time, we were doing the reviews. Take a break now, come back at quarter after. Okay, the next thing we're going to talk about, you have all heard about it, probably in a different form if you haven't heard about it in this form. This is section 12.4. This is called the normal distribution. Otherwise known as what? Actually, there's two other names. One you probably possibly also haven't heard of, called the Gaussian distribution. Or, which? The bell curve. Have you heard about a bell curve? Okay? If you haven't, that's all right. But if you look at a set of data, we're going to look at sets of data that end up approaching a curve that looks like a bell. Right? If you did that, doesn't that look like kind of like a bell? Liberty Bell or something? Okay? This is what the normal distribution is. Now, here's how it works. Let's say you took a survey of 100 people, let's say 100 men, and you looked at their heights. Okay? 100 random men in the United States. You looked at the heights of those men. Okay? It might look something like this if you did a little histogram. Remember, we got to do histograms. You got to remember how to do histograms for the test. Okay? And let's say it looks like this. Let's say it looks like this. Okay? This distribution of values, if this was between, I don't know, 5'5" and 5'6", and 5'6", 5'7", etc., all the way up to 6'2" or whatever, you might get a data set like this. If you looked at 1,000 men instead of 100, okay, it might look like this. You could actually get smaller little bars out of it. Okay, you get smaller bars out of it, and let's do one more like that. And then it might look like this, and then it might look like this, and it might look like this. Can you notice something different about this graph versus this graph, except that there's more bars in there? It's a little more average, right? Like the side here, if you folded this in half, right? This half would look a lot like this half. Like if you did a mirror up there or something like that. And if you did, instead of 1,000 men, you did 100,000. Okay? You'd end up getting little tiny little bars, and you'd end up getting something that looked more like a nice curve like that. Okay? You could have individual bars in there. Okay? But if you took 1,000,000 people or 100,000 people or something, and you did this, I didn't do that right in the middle. But if you did it right in the middle, the one side would look almost identical to the other side. This happens in lots of different types of sets of data. Height is a good one, okay? The average height of an American male looks like this. The average height of an American female would look very much like this too, except probably be a little lower, or I guess shifted a little bit, depending on, it would probably shifted a little bit if you took the same numbers, okay? Because women tend to be a little shorter, okay, on average. The interesting thing about this data is that the mean, right in the middle, not the men, the mean is the same number as the median, which is the same number as the mode. Okay? If you have enough pieces of data, well, you've got a mean somewhere right that's the average. And you've got a median, which is the number right in the middle, which for another average is the topmost little part of this. So it's the same, like the one that's the highest, which is the same value. And the mode, which is the topmost value as well, because the most of those numbers happen right there. Okay? So when you have standard deviations, you have the same amounts, or the same median, mode, and mean, which will give you a nice, good curve like this. Okay? Let me redraw it a little bit bigger. Got a couple interesting things that happen when you have a standard deviation. Okay? Here's what we've got. Something that looks like this. Okay? If you do a line right down the middle, like that, okay? And then we look at the standard deviation of this curve, okay? Look at the standard deviation of this curve. It might be right there. That might be the standard deviation. On the other side, because this is symmetrical, okay, it would be right about there. Okay? Standard deviation looks like that. Okay? And then you can go 2 standard deviations away, which might be here. And then 2 standard deviations away here would be about here. Doesn't most of the data fit between here and here? You're looking at those averages of all that value. Most of the data fits between there and there. Okay? In fact, 99.7% of the data is within 3 standard deviations. Okay? This would be 1 standard deviation away, 2 standard deviations away, and 3 standard deviations away. Okay? 1, 2, and 3. 99.7% happens between 3 deviations this way and 3 deviations that way. Okay? It also turns out that's within 3 standard deviations, 3 STs. 95% happens within 2 standard deviations. That means if you go from here, from this area here, I'll shade it in. Maybe I should use a different color, but anyway. Within 2 standard deviations is 95% of the data. And within 1 standard deviation, you've got, as it turns out, 68% of the data. 68% within 1 standard deviation. By the way, these graphs never touch the x-axis. In other words, if you were to take a sample of all the heights of all the people in the United States, or all the men in the United States, right? Well, you'd never get a person with 0 height, all right? You'd also never get a person with like 1,000,000 inches high or whatever, right? So this never hits quite 0, right? Well, I guess that was the wrong way of putting this one. I guess this side for heights might hit 0, but you're going to eventually have no people over here. But as far as the curve goes, the curve will never hit 0. It just keeps going out to more and more and more standard deviations. Okay? But the good news is 99.7% is within those first 3 standard deviations. We're not going to worry about the values outside of that. Okay? Who's the guy who plays for San Antonio? Sorry? I don't know, the tall guy. No, maybe not San Antonio. I forget the guy from China. What's his name?
Yao Ming.
Yao Ming, of course, Yao Ming. Yao Ming is like way out here somewhere, right? He's like one of those 0.001% dudes who's just way taller than everybody else, right? Okay? So there are some people way out here, but not many. Okay? 99.7% in the first third. How many are between 0 and 1 above the mean? What percentage?
34.
Yeah, if 68 are between here and here, that leaves 34% for here. Okay? And between here and here, well, this one's a little trickier. Let's add this up. 34% from here to here and here to here. And from here all the way to here, we said was 95%. Okay? So how much is left between, so 95 is all the way to there. Minus the 68%. 95 minus 68 is a 27%. in this section plus this section?
13.
So just this section is 13.5%, and this section is 13.5%. You can do the same calculation for the other one too. Some of the questions you'll get will ask you to figure out from here to here what the percentages are, or what the totals are, if you get values. So we'll practice those. Okay? All right. Okay. Here's an example. We'll use male adult heights in North America. If you have to be from like Denmark or something, they're higher. Okay? Americans aren't the tallest people in the world. Okay, I'll leave that right there. Male adult heights in North America are approximately normally distributed. This means normally distributed, bell curve, with a mean of 70 inches, 70 inches, okay, and a standard deviation, SD, of about 4 inches. Okay. Find the height that is 2 standard deviations below the mean. So we want 2 standard deviations below the mean. It's actually pretty easy. 1 standard deviation below the mean is 70 minus 4. So 60, so that's 66. And then 2 standard deviations is another 4 below. So the answer is just 62 inches. Okay, that's 2 standard deviations below. 3 standard deviations below would be what? 58 inches. What's 58 inches in feet? 58 divided by 12. 4 foot 10? So 4 feet 10 inches. If you know a male who's only 4 feet 10 inches tall, that means he's 3 standard deviations below, which makes sense because we know 99.7% of people are between the first 3 standard deviations. If you're shorter than 4 foot 10, you're a pretty short dude, right? And so, not that it's a bad thing, obviously, but you're outside 3 standard deviations from the mean, if the mean is 70 inches. Question? Question? No? Okay. Now, flip over that formula sheet I gave you. On the back of that, there's this thing called Z-scores, and I know you've all been curious about what that means, right? A Z-score simply describes how many standard deviations a data item is above or below the mean. Okay? So, a Z-score, the Z-score describes how many standard deviations a data point is from the mean, either above or below. We said that 62 inches was 2 standard deviations below the mean. What's the Z-score? Nope. Nope. This is easier than you think. You're overthinking it. We went from 70 inches to 62, and we said that was 2 standard deviations away. Well, the Z-score just tells how many standard deviations it is above, which is positive values, or below, which is negative values. So the Z-score for being 62 inches, which is 2 standard deviations below the mean, is negative 2. It's that easy. Okay? We'll talk about percentiles in a minute. All right.
So you're saying, what was the question you had?
Okay, all I said was, here's what I asked. I said, okay, we figured out 62 inches was 2 standard deviations below the mean. Okay, we said the mean is 70, the standard deviation is 4. What height is 2 standard deviations away? Well, it's 70 minus 4 minus 4, 2 standard deviations away. 62 inches. Right? Okay? 62 inches has a z-score of -2 because it's 2 standard deviations below the mean. That's
So
all
when
I'm
you say
saying.
deviation below mean, you want the negative.
So I want the -2 value, yeah. 2 standard deviations below the
Not
mean is the negative.
percentile.
No, not percentile. We'll get to that. We'll get to that. Okay, I'm going to erase this thing because it's taking up too much space. Here's how you figure out the z-score. Okay. Pretty easy. Z-score equals the data item, that's the one you're looking at, minus the mean divided by the standard deviation. That's all you have to do. That is also on your formula sheet. The last little formula on there. The z-score. Data item minus the mean divided by the standard deviation. Okay. Which is exactly what we had before. We went from 70 inches, which is the mean, and we said 4 inches is the standard deviation. And we wanted to know the z-score for somebody who was 62 inches tall. It's easy. 62 minus 70, because that's the data item, minus the mean, divided by standard deviation. Okay? That makes sense? Yeah. 62 minus 7 is -8. Divided by 4 gives you -2. That's standard. That's the z-score. All right. Let's do a couple practices on this. Weights of newborns. Normally distributed with a mean of 7 pounds. 7 pounds. That's the mean of newborns. Okay? And it's normally distributed. And the standard deviation is 0.8 pounds. 0.8. Find the z-score for 8 pounds. Plug it in. 8 minus 7 divided by 0.8. 1 divided by 0.8 is what? 1.25? So, a baby that has a weight of 8 pounds is a little bit more than 1 standard deviation away from the average baby. Okay? Meaning that he's in that 95% versus 68%. That's cool. 98% are there. Anybody else besides me? Was anybody else besides me a preemie? You're a preemie? Do you remember how big you were? How many pounds you were?
Tiny.
How tiny?
6, I think.
6 pounds? Okay, so let's find out your z-score.
6 or 7.
What's that? Let's say you were 6. 6 pounds. 8 minus 6 is 2 divided by 0.8. What's your z-score? 2.5. Believe it or not, you were still within that 97%. Okay? I believe I was 4 pounds 6 ounces when I was born. And that was a long time ago, back when they were like, it wasn't so easy to keep people alive when they were that small. I think they gave me a 50-50 chance of living. Here's why they gave me a 50-50 chance of living. What was my z-score? 4.5, let's say. 4.5. 8 minus 4.5 is 3.5. 3.5 divided by 0.8. 3.5 divided by 0.8 I had a z-score of 4 point, actually negative. Sorry, I've been doing this wrong. We have been doing this wrong. You guys aren't fixing me on these. Let's do yours again. You said you were 6 pounds? Actually, yours is going to be the same. 6 minus 7, negative 1 divided by 0.8 means you were negative 2.5. Still within that thing. 4.5 minus 7 is negative 2.5. Negative 2.5. Negative 2.5 divided by 0.8 is what? Negative 3.125. Meaning that more than 97% of more than 97% of babies are bigger than poor old Chris is 4.75 or 4.5 pounds, right? So it's no wonder they're a little worried, because there's it's rare to be that small anymore. Okay? Now you know how to figure those things out. Questions on those? All right. I turned out okay. My mom's very thankful for that, I guess. All right. Well, I would say I turned out okay because my answer was okay. The z-score also measures a data item's position on that normal distribution. So we have the normal distribution, okay? Like this. I don't know why I did it like that. Do it like this. There's your normal distribution, okay? We know that this is right, let's say that's right in the middle. Let's say I can draw straight, okay? What's the z-score of that right there? This is the distribution, and that's the mean. Yeah, the mean is 0, so no matter what the square root is, or sorry, not the mean, the value minus the mean is going to be 0 divided by whatever the standard distribution is. That's the z equals 0. Okay, now obviously one standard deviation is z equals 1. One standard deviation this way is z equals negative 1. The other measure is the thing that's on your formula sheet, which is the percentile. Okay? If 10% of items in a distribution are less than a particular value, okay, then we say the data is in the nth percentile. Nth percentile. Okay. If you do better than half the people, that means that 50% of the people did worse than you, meaning you are in what percentile? 50th percentile. If you got 100 on the test, and that was better than all the other people, you are in the 100th percentile. Well, 99.999 is tough to be in the 100th percentile, but I guess you could be in the 100th percentile. If everybody else did worse than you. Okay, if the percentage of people that did worse than you was everybody, that would put you in the 100th percentile. Okay? If you score 75% on some normally distributed thing, like the SATs, there's enough people that take the SATs that it becomes normally distributed pretty easily. And they force it that way with the way they grade it too. You know, it would be that way normally. 75 percentile, if you were in the 75th percentile, 75th percentile, okay, what does that mean? 75% of people did worse than you. That's what it means. 75th percentile means 75% of people did worse than you. Okay? If you look on the sheet, you can convert from percentile to z-value, and z-value percentile, and that's the only reason this little chart exists. Okay? If you are in the, let's see something that's easy here. If you are in the, let's see, 81.59 percentile, what's your z-score? 0.90. You can read it straight off the chart. Okay, so I could ask you that. I could say something like, here's we could do the same exact example before with the heights. 70 inches with a standard deviation of 4 inches. Okay? 62 inches is what percentile? We said, first of all, we calculate the z-value by doing 62 minus 70 gives you negative 8, divided by 4 gives you negative 2 for the z-value. Okay? And if you look on the chart, negative 2 says what? 2.28 percentile. 2.28 percentile. Okay? What that means is most people are taller than you, right? Because that means that 2.2%, 2.28% were shorter than you. So that means 97% are taller than you. Okay, that's how you figure those out. It turns out that there are other types of distributions. Okay? The normal distribution is not the only one. Okay? We have, let's say you look at earnings. We did this a couple last week too, a little bit. You look at earnings, okay? Most people earn some amount of money, okay? Like that. Some people earn lots and lots and lots and lots of money, but there's not that many of those people, okay? So what this says, what this looks like is something like this, where you have some people way out here making like $1 billion or $1 million, making $1 million, right? Most of the people are going to be over here, but the people that are way over here skew the values that way enough because there's no maximum amount of money you can make, right? You can't be like, you're capped. It would be kind of interesting if you were. Like, well, I don't know if it ever used to be that way. Way back in the day when income tax started, the more money you made, and this is still the case to some extent, the more money you made, the higher your tax bracket became. So if you made over, I don't know, back in like 1927 or something, if you made over $1 million, anything over that $1 million was taxed at I think a 90% rate. So if you made $2 million, that second million, you'd only get to take away 9–10% of that. You'd only take away $100,000, even though you made $1 million on that extra million. And you know, back then they were like, well, that's kind of almost like capping the amount of money you make. Because really, you can make a lot more money out of them. You're only getting 10% of your money out of it. They fixed that because rich people have to be powerful. So the powerful people changed that. But it's not the case anymore. But the point is that you can make as much money. There can be Bill Gateses out there who make billions and billions of dollars. They skew the numbers such that there's only a small proportion of them, but they make lots and lots of money. Okay? So that's skewed that way. There are also ways you can skew things the other way. Okay? This is an example of example you guys just did a few minutes ago. If you look at all your surveys that you guys filled out, I don't even know if they have, do they have like numbers you can rank, or do they say like, I don't know, worst to best or something, and there's like 5 categories or whatever? You can look at those categories, you can put a number, you can average all those and put a number on the teacher, right? If you look at all the teachers all over UMUC Europe, right, the average of those grades generally would look something like this. Meaning what? Meaning most people aren't going to be mean to their teachers when they give them the grades, right? They grade most people fairly well, and then some teachers are kind of terrible and they give them the bad grade. So it's you know, you kind of want to be over here if you're a teacher, but that's what it is. Okay, so there are different types of distributions as well. Okay, all right. Let's see. I believe we are done for the day with the teaching stuff. Okay? Oh, you know what? There is one more section. I lied. Really quick one, actually. One more section. Sorry, that was really mean of me. I'm glad you already filled out the surveys. Okay. Sorry, I was looking at the one more thing. Yeah, there's one more really short example. Okay, here's a problem-solving example. So try this. Try this with a normal distribution. Okay? All right. We all had to get our cholesterol tested before it mobilized, right? In fact, there was a guy who was supposed to be the CJTFO at J3. Didn't come here. We thought he was going to be the next J3, but his blood pressure was too high, so they didn't let him go. In the Army, that's kind of a bad deal. He was really looking forward to it, I guess. For young men, cholesterol is normally distributed with a mean of 178.1 milligrams per 100 milliliters. I guess that's in your blood. 178.1 milligrams per 100 milliliters. With a standard deviation of 40.7 milligrams per 100 milliliters. What percentage of young men have a cholesterol level greater than 239.15? What percentage have cholesterol greater than 239.15? Question. Okay. Figure that out.
You said 239?
Two. Sorry, I wrote 293, but I meant 239.15. What percentage have cholesterol greater than 239.15? Try that. Hold on. You're really fast. Hopefully you're calculating the z-value. You didn't get it right. That's not the answer. Oh, which one? This one? Good. You got 1.5 right. Good. All right. Does this answer the question?
No.
No. That's how many people were lower than 239.15. We want greater than that. Okay? So we have to find the answer, which is 100% minus 93.32%, which is 6.68%. And we had a first shot. Good job. That's how you're going to end up solving them. These are the kinds of problems you might see on the final exam, where they ask you one question, and you have to go through a bunch of steps and figure out which ones are the right ones to do before you get to the right answer. Okay? Well, yeah, I'll still grade it using, I'll grade it partial credit, but the point is you gotta know all the partial credit. What's that?
7.3. 7.23. That's a greater sign.
Oh yeah, it's a greater than 7. Yeah, your cholesterol was 7,239, you'd be in trouble. I don't think you'd be breathing still. Okay, this next example is actually it's another tricky one that you have to use a couple different things to figure it out. Okay? I'll write it up at top. In a normal distribution, the hours worked per week, okay, not really here I'm afraid, is 44.6 hours with a standard deviation of 14.4 hours. Okay. So 44.6 hours per week. 44.6 hours per week equals the average. Okay? And 14.4 hours per week equals the standard deviation. I want to know what percentage of individuals work between 21.56 hours and 69.08 hours. 21.56, 21.56 is less than or equal to X, which is less than or equal to 69.08 hours. That's the question. What percentage? Okay. Now you got to do some calculating on here. I'll give you a hint. You're going to have a z-value. You're also going to have another z-value. It's actually a pretty big hint. Can you see her here? I ended up with 90.06%. You guys get this one?
I'm reading.
Read it. Why don't you try it? You gotta try this stuff. You gotta try it. This isn't really that hard, it's just a matter of applying the principle here. First thing I did, I said the z value of the lower one, 21.56 minus the average, 44.6, divided by 14.4, gives me negative 1.6 for the z value. I did the same exact thing for the upper value, and the only number I changed was the 69.08. Same value, or same system. 1.7, I looked at the percentiles for those two. Negative 1.6 was in the 5.48 percentile. And the 69.8 was in the 95.54th percentile. And I subtracted those. Because 5.48% were lower, right? And 95.54% were below the other value. If you subtract the two, you get the value right in the middle. Percentile right in the middle. That was the part that took a little bit of thinking. Right? 90.06%. If you want, there's two charts you can look at. Page 723, there's a little table that tells you how to do this. And then 724 gives you another way of looking at it with the actual bar curves, or bell curves. All right. Any questions on this stuff? That was it. We have one more section tomorrow, and then we are done with the new stuff. Okay? Done with the new stuff. Here's what I'm going to do. I've got a whole bunch of stuff to work on. Please work on the stuff. I would start with the practice sheet. It says 12.1 through 12.5 practice. Then I would go into practicing the exam stuff for the exam next week. And then if you do all that, you can work on the final exam practice. And I will answer any questions you guys have.